Hello friends, this is our fourth lecture. In previous lectures we have studied the content in the chapter MOSFET and DC analysis, construction of MOSFET and its working. We have studied the working of N-channel enhancement MOSFET. What is the VI characteristic of N-channel enhancement MOSFET? In short, N-channel E MOSFET is called NMOS. And what are the conditions for NMOS to be in saturation, to be in cutoff and to be in non-saturation region? And what are the applications of NMOS transistor, or what should be the working region of transistor when it is used as a switch, when it is used as an amplifier? We have discussed in short. Today we are going to study PMOS, P-channel enhancement MOSFET. We are focusing enhancement MOSFETs. Why this P-channel enhancement MOSFET or PMOS is important? We are having CMOS inverter in our syllabus. To understand the working of NMOS and PMOS together in a device, inverter, we should know each and everything about the PMOS transistor also. I am going to draw the biasing diagram of PMOS transistor. First, we will begin with construction diagram. So, we have P plus regions as a source and drain in PMOS. So, P plus constitute two regions, source and drain. Oxide layer, already we have studied the thickness of this oxide metal layer, width and the channel. So, it is the plus a gate and it is source, and this terminal is the drain terminal, and here we have channel formation. Okay, channel will be induced here according to the voltage on gate. Now, here we have substrate, P type substrate. Okay, and what is the voltage in P MOSFET? Sorry, here it is N type substrate, and one terminal from this is the body, substrate terminal from body. So, here in P channel E MOSFET, negative voltage is applied, negative bias is given to the gate. So, it is, I am showing the DC battery. So, it is minus and plus, minus plus. So, it is VSG, sorry, VSG, not VGS here, and to the drain we are applying again negative. So, it is minus and plus, and the name label of this is VSD. We are not using VDS here, and gate source is at ground. Okay. So, this diagram is a bit confusing. Now, I will draw one more diagram. So, I am drawing here vertical structure of PMOS, and we are applying DC voltage across the three terminals. So, it is the body, and we have heavily doped two structures deposited here. So, it is P plus and P plus, and it is oxide layer, and this one is N substrate, and one terminal is taken. So, this is the substrate. Let us call this as a VB. We should maintain the body voltage at a particular potential, and here we have metal. and it is gate terminal, and source connected to this via metal, and here it is the drain terminal, and it is source terminal. Now we have to apply such voltage, the current will flow through this. Okay. With respect to this diagram, we can draw this, it is Vs uppercase letter, because all the quantities are DC here. Gate is provided with negative bias. So here is minus plus, so this voltage is with respect to source, with respect to gate, and this source and drain. Now see here it is negative and plus is given to the source here. In this diagram we can complete this and we can understand what is the meaning of that. See this. It is negative terminal and positive terminal is connected to source and negative is connected to drain. Completely the connections, the biasing diagram is complementary to NMOS. The polarities are reversed. So here source is at positive potential and here the source is at positive potential, and this one we can ground this portion here. It works like this, and drain this one. Now where the body should be connected, substrate connection should be at higher potential. Why? Because so this region is having depletion region. So it is N, there is a formation of diode PN junction. The current is not going to flow through the substrate, the body of the transistor, but it should be reverse biased. So it is connected at higher potential. So VB should be higher than, so we can make a general equation. So VB should be always greater than 0. The substrate voltage must be greater than 0, okay, in case of PMOS device. What is the label of this? So it is VSD. We are not using VDS here, okay. NMOS it is VDS, here we are using VSD. So VSD versus ID, okay, and VSG is the gate parameter, gate voltage, the parameter which controls the drain current here. Now what will happen when voltage is applied, this voltage is applied, the current will flow. What is the direction of current? Same operation like NMOS here. See, the direction of current is different. See, it is at higher potential. Now see, positive is applied here. So due to positive charge, electrons will repel this. So before that there should be channel. The negative voltage on this gate will create a channel, okay. It will collect the holes as a minority current carriers in this N type of substrate, and they will deposit here, and the channel will form because of inversion layer. When the concentration of holes is enough to form a channel, okay. So who decides the concentration of charge carriers? It is the threshold voltage. When the voltage on gate is greater than threshold voltage, the inversion layer is formed below oxide layer, and these electrons are repelled due to this positive charge and they attracted due to this negative polarity on drain, and the holes from this P plus region, source region, they move towards this drain region, okay. Here the holes is the main source of current, therefore the direction of current is like this, okay. When electrons flow from source to drain in case of NMOS, the current flows opposite to the direction of movement of electrons, but here the holes moving in this direction and current also moving in the direction of movement of holes, that is the direction of conventional current. Okay, it moves in the direction of movement of holes. And what is the direction of movement of holes here? Source to drain. So, current is entering the device. So, it is plus, the current is flowing like this. Okay. But someone will ask what is the substrate current. So, IB DC current, okay, substrate current is 0. Now, what is the gate current? Gate current is also 0. Here we can make a point. You should remember this, that IG DC current, gate current is 0. Okay. So, this is the cutoff region of the device. Okay. We can make a statement that in cutoff state gate current is 0, okay, substrate current is 0 and the drain current is also 0. Fine. So, these are the simple connections. We can understand the working of PMOS device from this diagram. Now, let us draw the VI characteristic and label the different regions, cutoff region, triode region and saturation region, and we will write equations for the currents in triode region and saturation region. Now, I am going to draw one more connection diagram by using symbol of P MOSFET. So, generally source is drawn this upper side in case of PMOS, and in case of NMOS it is shown lower side. So, it is the drain, source, gate. Now, according to the previous diagram, we can show the DC biasing voltage. Gate is at negative potential and here it is at positive potential. So, it is, this voltage is VSG. Why VSG notation is used? Because it is with respect to higher potential is connected to source and negative potential, negative terminal is connected to gate. Because of this it is used. And this voltage, this one is VDG, okay, and it is considered plus here and minus here. Okay, we require these voltages for developing the biasing condition for the devices. So, it is the drain terminal. Now, the supply between source and drain. So, source is at positive potential and it is the drain at negative potential. It is plus minus and the direction of current is plus to minus. So, here somewhere we can show the ground point for the circuit, okay, and see, it is flowing like this, the current is going into the device, so it is coming out to the ground, this point. Okay. Characteristic, VI characteristic of PMOS transistor. Now, what is the current here? So, it is the drain current. We are not writing the source current here, although it is entering from the source, we are writing drain current ID, it is 0, and this is VSD. I will write inside this. So, it is VSD, not VDS. So, it is VSD, and this current is microampere. Because the device dimensions are very small, it is on integrated form, therefore, the currents and voltages are of small amount. Now, see, what is the VSD? VSD is negative, say it is minus 1, minus 2, minus 3, minus 4 and minus 5. The current is not negative. Okay. So, this is the reverse voltage, we are taking negative polarities, but the current is positive. Current is function of time, it can't be negative. Therefore, we can write here as 50 microampere, 100 microampere, 150 microampere and 200 microampere. Now, see, what is the cutoff region? What is the condition for that? So, cutoff region. Cutoff region, threshold voltage, the gate voltage is less than VGS is less than VTP, less than VTP. So, threshold voltage of PMOS device is denoted by VTP. So, it is the threshold voltage. What is the threshold voltage of PMOS device? -1, -1.5. So, it is the negative voltage. If it is less than this, the device remains in off condition. And what is the drain current? So, ID is almost 0 and there is no other current in the device except the very small amount of leakage current. Okay. Now, when the voltage is greater than this one, now here take this, in what sense it is less? Okay. It should be greater than -1. Okay. Greater than means not positive value, it is -1, -2, -3 in that sense. So, first curve we will get here, the voltage is greater than -1, the device turns on and this is the point. So, here the device starts saturating. So, this voltage is VSD, saturation voltage. And what is the amount of voltage should be maintained at the drain? It should be VSD should be greater than or equal to, it is VSG minus mod of VTP. When we maintain this voltage at the drain, at that time the device is driven into saturation, the channel is pinch off and the current remains constant. So, this condition VSG is the highest negative, say it is -5 volt. Okay. And here in this case, if we draw the first characteristic, so this, so it is greater than VTP. So, it is VSG is equal to, it can be -2 volt. Okay. And we get a family of curves. Here we get a family of curves like NMOS device. Okay, -4, -3 and so on. This one. So, this is the condition required. Now, what about this region? When voltage on gate, voltage on the source and drain is less than this voltage. Okay. When voltage is less, when VSD is less than VGS, I will write here, when voltage on drain VSD is less than VSG minus mod of VTP, at that time the device works in triode region. Now, what are the equations of current in triode and saturation region? Okay, I will erase this. In cutoff region, we will write systematically. Cutoff region VSG is less than VTP less than -1. Okay, VTP equal to -1. If VTP is equal to -1 is the threshold voltage of PMOS device and it is less than -1, the voltage on gate, the device remains in cutoff region and drain current is 0. So, this is the off state of the device. Second, triode region. When the device will be driven into triode region at this condition, when VSD okay, and it should be provided. Gate voltage is important. So, VSG is greater than or equal to VTP, means we have applied the voltage on gate greater than this voltage and it is in on condition. Okay, the current is changing according to the change in VSD, okay, not VSG. VSG is required, it should be greater than the threshold voltage required to turn on the device. Now, this, what is the drain current here? And we can write one more condition here, it is the voltage on source also should be maintained, it should be less than VSG minus mod of VTP. VTP is negative, therefore, every time we are taking the modulus of VTP. Now, what is the drain current ID? So, ID is equal to, so it is Kp into VSG minus VTP, we are not taking mod here, VTP into VSD minus VSD square by 2. So, this is the current flowing through drain when the device is in triode region. Now, second one is the most important is saturation region. So, here we will write the drain current equation. When the device is in saturation, what is the drain current? Saturation region. So, it is ID, and what is the condition to be in saturation? So, VSD should be greater than this, should be greater than or equal to VSG minus mod of VTP. Here we are taking mod. So, this voltage is called as overdrive voltage. Okay. What is overdrive voltage of MOS transistor? See, VTP is the minimum amount of voltage required to turn on the device. Okay. Once the device turns on, the drain current starts flowing and the drain current changes linearly with VSD as well as the gate voltage. Okay. So, here it is the linear characteristic, the characteristic is linear and the device works as a linear, in linear mode the device works, we can say like this. Okay. But from this it is the non-linear. So, it is the drain current equation tells the behavior of the equation. So, it is half Kn dash ratio of width to length and it is VSG minus VTP square. So, this is the equation. We can write this as, see, Kn dash is process conduction parameter, whereas Kn is conduction parameter. Kn is equal to, we can take this as Kn dash W or L. We can write this equation as ID is equal to, so it is half Kn VSG minus mod of VTP. Okay. So, this is the drain current in saturation region. Already I have explained what is the behavior of transistor in saturation. ID depends upon the gate voltage, it is the function of gate voltage and it is the square law equation. Okay. And it changes according to the change in the gate voltage, it is desired feature of the transistor. So, this is all about the PMOS device.